we were able to generate, measure, and move domain walls in an antiferromagnetic system. What this means is you could use this as a potential for a memory device, where you can move a domain wall to define a bit which is either 0 or 1. To generate a domain wall in an antiferromagnetic material, we apply a magnetic and an electric field. By applying them parallel, we manage to create a certain orientation of the antiferromagnet. By applying them antiparallel, you get the opposite orientation. Between these two, you generate a domain wall. So in order to measure the domain walls, we use a technology that's been developed in our group based on diamond defects, specifically one which is called the nitrogen vacancy, or NV center. So here you have a nitrogen and a vacancy, and this creates a defect which is sensitive to magnetic fields. So by bringing this defect close to your antiferromagnetic surface, you can measure the stray magnetic fields that are produced, for example, from the domain wall. We found out that we can control where the domain wall lies on the surface. And to do this, we etch the surface such that what's left behind is just small square areas. With this, the domain wall interacts with these squares, and we can use the squares to direct where the domain wall goes. We also found that by heating the sample locally with a laser, you can move the domain wall repeatedly over these structures. Based on what we've been able to show, this gives us sort of a proof of concept of a type of antiferromagnetic memory. The small squares define the bit location, and by moving the domain wall left or right from these squares, you can set the bit to either 0 or a 1. So this way you get a rewritable antiferromagnetic memory. The advantages of these kinds of antiferromagnetic memories are that they would use a lot less energy, and they have the potential to be much faster than the current forms of, for example, hard disks that people use today.